Grading text is static analysis. The model reads and scores tokens. But evaluating a working web app means judging an artifact that actively executes. An ICLR 2026 paper mapped this discrepancy. Grading functional web apps, expert humans agreed 84.5% of the time. GPT 4.1 agreed only 70.3%, a 14-point deficit. On text benchmarks, researchers fight over tight margins. This 14-point gap is an extreme anomaly. The transition from static text to functional software forces a complete shift in the mathematical object of judgment. Old evaluation pipelines break the moment the artifact has to do something. I'm the host of Bearded AI Guy. Today we're looking at the WebDevJudge benchmark, brought to my attention by the human architect. This passed top-tier peer review to secure an oral slot. The field is officially documenting a systemic failure in how we evaluate code. Standard text evaluation functions reliably because it relies on judging meaning within a single, isolated representation. Web judging demands an entirely different architecture, cross-representation consistency. The judge maps query intent to code structure, to rendered output, to runtime states. Trust fractures if one layer lies. A button might look correct, but if the runtime fails, the entire application fails. To prove this mathematically, the authors constructed a strict benchmark. They started with 10,501 raw queries and aggressively filtered out duplicates and unsafe prompts. They then deployed the remaining code in a standardized Next.js environment, enforcing strict HTTP status and screenshot checks, leaving 654 mathematically verifiable instances. This rigorous distillation explains why successes on conversational tasks, like MTBench, fail to translate to engineering. Functional web artifacts expose representational breakages that conversational benchmarks never test. To evaluate a complex web application, you must deconstruct it into atomic, verifiable components. Asking a language model to grade a functional app without a rigid checklist forces it to rely on fuzzy aesthetic preferences. It guesses based on what looks generally correct, rather than verifying what actually executes. Researchers quantified how poorly this intuition performs. Without guidance, baseline inter-annotator agreement stalls at an unusable 65%. By introducing a strict rubric tree to separately check intention, static elements, and dynamic interactions, agreement drives securely above 90%. Reliable evaluation of working artifacts requires stripping away subjective human aesthetic judgment and replacing it with rigorous binary software quality assurance. When evaluation pipelines fail, the immediate engineering reflex is to provide the AI judge with visual context, screenshots, alongside the source code. Judging an application purely by its screenshots carries the exact same risk as evaluating a sculpture from a photograph instead of a code reviewer reading the source. Let's apply a technical lens to this assumption and examine GPT 4.1's pairwise comparison data. This visualization isolates modalities. Image-only evaluation underperforms at 60.55%. Reading the source code without images jumps accuracy to 69.57%. Counterintuitively, combining code and images only pushes the margin to 70.34%. In absolute scoring, adding visual context actively destabilizes the model's calibration. But relying strictly on a code-only reviewer presents a severe, unmitigated risk. The model analyzes the syntax and concludes the feature works, but never attempts to execute the application at runtime to prove it. The proposed industry fix is to deploy autonomous AI agents to physically interact with the UI, verifying if elements trigger correctly when clicked. Implementing this execution grounding creates a harsh mathematical trade-off within the evaluation pipeline. This matrix shows GPT 4.1 code-only evaluation overcalls feasibility, reaching a high recall of 90.0, but lagging on precision at 72.1. Deploying the UI TARS 1.5 agent pushed precision to 82.4, but recall plummeted to 70.3. The agent frequently fails to locate visible elements, misinterpreting the UI entirely. Deploying an execution-grounded agent doesn't solve the evaluation problem. It simply replaces the evaluator LLM's code hallucinations with the agent's perceptual and navigational failures. The deepest algorithmic flaw in modern LLMs is the stark divide between ranking two items against each other versus scoring a single item alone. Models reliably identify which implementation is superior, but structurally lack the absolute calibration required to assign an accurate grade to a single answer. The hard data on intermodel consistency exposes the severity of this issue. For pairwise comparisons, model consistency remains robust at over 75%. In single answer grading, consistency violently plummets, vibrating between 50 and 65%. Even pairwise rankings hold structural errors. GPT 4.1 shows a 15.8% second position preference. Swapping order mitigations fail to correct aggregate scores. Zooming out from the granular benchmark data, engineering teams need a functional architectural mental model for deploying LLM evaluators in production. Ask the first critical question: what specific representation does the judge actually see? Is it parsing code, analyzing screenshots, or tracking runtime state? Ask the second question: what exact dimension is the judge attempting to score? Intention, static elements, or dynamic interaction? Ask the third question: what is the systemic cost if this specific failure mode triggers in your live application? A positional bias error in a casual chat interface is a low-stakes annoyance. A code grading system silently verifying a completely broken database transaction is a catastrophic failure. The WebDevJudge paper proves that the standard industry recipe, prompting a strong model and adding screenshots, is entirely insufficient for evaluating functional software. We can anchor this entire thesis in one canonical example of cross-representation failure from the research. On the left, a rubric structness dictates a section labeled organization. On the right, the rendered application delivers a block labeled presentation. An LLM-judge routinely mistakes the superficial visual layout of the word presentation for fulfilling the structural requirement of organization. Creating software that visually looks right and creating software that executes perfectly at runtime are completely different skills. Until our AI evaluation pipelines evolve the capacity to measure that exact difference reliably, expert human judgment remains the only accurate standard in the room. If you've shipped an LLM-judge system into production, drop your war stories in the comments. I want to know exactly what broke first. I highly recommend reading the human architect's full breakdown of this paper for a deeper study into the evolution of evaluation architecture. I'm the Bearded AI Guy. Thanks for watching.